Video Lecture 1.2, Solar Radiation. Solar radiation is the source of energy that drives most environmental processes acting at the surface of Earth. And so very important is the variation of solar radiation on Earth's surface then causes the variations of all the various things we're going to talk about later this semester and throughout the semester. So this is very much a building block for things we're going to talk about later. And so variation of solar radiation on Earth's surface is going to cause variations in temperature, variations in wind, variations in moisture and precipitation. All of this is fundamental because then this causes variations from place to place in terms of weather and climate. Weather and climate also then affects vegetation type, soils, which then also maybe affects whether or not you have rivers in your area or your area is quite dry, which is then going to affect erosion and all these various things we're going to talk about throughout the semester. And so key to kickstarting all of this is solar radiation from sun to the earth. The key solar input to life is the electromagnetic energy. And so the sun sends to Earth the electromagnetic spectrum, this electromagnetic energy of various wavelengths. And so the sun radiates, or sun sends to Earth, shortwave and longwave energy, whereas the Earth then radiates back outward, only longwave energy. What is shortwave? What is longwave? I'll get to that here in a minute. So the sun sends to Earth shortwave and longwave, whereas the Earth radiates back out only long-wave energy. Shorter wavelengths have higher energy, and vice versa. Longer wavelengths have lower energy. So get that stuck in the head. And so what do I mean by long wave and short wave? Well, here we can see what they visibly look like. And so at the top would be a long wave, at the bottom, short wave. And so, of course, learning from what we just talked about, long wave at the top, lower energy, whereas the ones as you get closer to the bottom, closer to the short wave, higher energy. And so just to even visualize this, kind of what I've been describing, sun sends to Earth, solar radiation. So let's look at that solar radiation. Let's go and try to understand, well, what is inside that orange arrow? Okay, and so what we're doing is we're looking inside solar radiation. We're trying to get a peek and understand it. And so that white box with what we see here in the middle is essentially all of the electromagnetic spectrum. Now, one of the characteristics of the electromagnetic spectrum is we can only see just a small little sliver of that. That's visible light. So that's what's there in the middle. So much of the solar radiation, much of the electromagnetic spectrum are things that are invisible to the human eye. So at the top you have the highest energy, so gamma rays, X-rays are going to be the highest energy, shortest wave, whereas at the bottom we have infrared, thermal infrared, microwave, radio waves are the lowest energy, long wave. And so here's another way. We're going to see these arrows on future slides, different colors, and so I'm showing you this now more for that purpose. But once again, gamma rays found on the left-hand side. Gamma rays, short wave, high energy. Gamma rays and X-rays. There's a reason why when you go and get an X-ray that they put all that gear on you, because those X-rays are quite harmful. That's why they put that stuff on you, just to protect our bodies. Of course, ultraviolet rays, if you look at sunblock, sunblock is there to protect our skin from ultraviolet rays. Visible light, that's what we can see, all the colors of the rainbow. So visible light, we can see that. So that's the one part of the spectrum that human eyes can actually see. Infrared, we can feel infrared. We can't see it, but we can feel it, and we can feel it in terms of heat. So if you think about the electromagnetic spectrum, here's how it's broken down. 8% of sun's radiant energy is found in the gamma rays, X-rays, and ultraviolet rays. 47% found with visible light, and 45% with infrared. So like I said before, the sun radiates to Earth, both shortwave and longwave, but then the Earth emits most of its radiation as infrared, or longer wavelengths. Although we can't see this, our skins are quite sensitive to it. We often think of infrared radiation as heat. Here we have the key term, insolation. And so insolation comes from incoming solar radiation. It's the way we measure the amount of solar radiation energy is found at a given place. And so the insolation from the sun to the earth flows at a constant rate. However, like I said before, it varies from place to place, but also from time to time. Like I said on the previous slide, there's an uneven distribution of insolation on Earth's surface. And so why is that? It's because Earth is curved. Earth is a ball. Earth is a sphere. It is not flat. And so this curvature creates a situation in which the tropics receives 2.5 times more insolation than the poles. Some key terms. The subsolar point. The subsolar point is the point where insolation is perpendicular or 90 degrees to the sun's rays. And you'll see what I mean on following slides. The subsolar point, it does not stay in the same spot on Earth's surface the entire year. Instead, it varies, it moves, it migrates. So as that migration changes, the subsolar point's declination changes. And declination is just simply the latitude of the subsolar point. Like I said, it varies. And it varies corresponding with some key lines of latitude from Map Quiz 1. And so it migrates between the Tropic of Cancer, 23.5 degrees north, and the Tropic of Capricorn, 23.5 degrees south. So we think of each of these arrows as solar radiation, as an individual sun ray, so to speak. And so each of these, like I've said before, is a constant. However, on Earth's surface, it varies. And we can see that represented here with these arrows in the teal lines, those blue lines representing Earth's surface. And so you can go ahead and see which one of these is the subsolar point. And you should select this one right here. And so the subsolar point is the most direct. It is at a 90-degree angle or perpendicular to the surface. And I want you to go ahead and also look at the other arrows and the other angles and kind of their characteristics related to the red one. So if you go back and look at the previous slide, you'll notice that the arrows and Earth's surface, they vary as far as their position relative to each other. And so one of them, the subsolar point, the red one, has what we see at the top, that 90-degree angle, perpendicular. And so that's going to be where we find the highest energy is in those direct 90-degree angles, where it's the highest number, highest angle, closest to 90. Whereas the closest we are to 0, as we move down to the bottom, lower angle, we're going to have lower energy. So like I said before, incoming solar radiation, it's constant. The key to understanding variation is Earth's curvature. So here we have a high angle and a low angle to kind of emphasize what I've said on a previous slide. So a high angle, low angle. Both of these are the same width. However, if we look on the Earth's surface, we see the lower angle, it's more spread out. It takes up more space there on the Earth's surface on the green line, whereas the higher angle, much more concentrated. But both of them are the same. Both of them are the same width. And so we can see how the lower angle covers more surface area than the higher angle, which is key to understanding what we're going to talk about on the following slide. This illustration, once again, showing two flashlights held at different angles. Flashlight 1 held directly above the surface at a perpendicular or 90-degree angle. Leaves a much more concentrated beam of light than flashlight 2 would say, maybe at a 45-degree angle, leaves a less concentrated, but more spread out. So think of this as an analogy to what we've just seen beforehand. Now, translating these flashlight examples to Earth's surface, once again we go back to what we've talked about beforehand. 2.5 times more insolation on average in the tropics compared to the poles. And that makes sense now that we understand that's related to sun angle. It's related to where the subsolar point is compared to where you're located. And of course, places along the equator are going to have more of that direct solar radiation, that 90-degree angle, compared to places further closer to where we are in the what they call the mid-latitudes, 40 degrees north to eventually up to the poleward areas, where obviously they get a much lower angle. And so it's not so much related, like I've said in 1.1, it's not related to how close we are to the sun. Instead, it's related to where we are in respect to the subsolar point, has a key role as far as understanding solar energy at Earth's surface.